missed out on one that's quite fun. And it leads to these fantastic pictures of fractals. You may have seen, I intended to bring in a book by Peitgen that has sort of the beauty of fractals is his title. Has pictures of the Mandelbrot set, just amazing. And just, it's interesting mathematics, and it's mathematics of recent years. So I'm going to put off the wave equation and heat equation to the second lecture today, lecture 12, and discuss this one because it's sort of, so here's the general plan. You have some function, and you start at some point u0, and you compute f of u0, and that gives the next point. Then you compute f of u1, and that gives u2. And then you keep going. So un is, so to speak, f of. It's we're taking, well, the mathematical word is composition. So let me just put up u2. So you see u2. U2 is f of u0, because that's u1. So we're repeating the same operation f. And it's simply amazing what you get, and it's a topic that was not very much studied until we could actually execute it. So I guess what I'm hoping, this is a sort of partly a fun lecture, but you could experiment with some f's. They don't have to be very complicated. Here's a linear one, and we'll quickly see all the possibilities there. But it's really nonlinear functions f. You see, suppose f is a quadratic, which is, you might think, okay, quadratics can't be too hard, but the best minds in mathematics have gone in recent years to understanding what if f is a quadratic. So we have a quadratic function of u0. Then when I do another one, it's a fourth degree function, because it's a quadratic of a quadratic. We're squaring squares. Just already at u3, I'm up to 8th degree, and just, you need new ideas to get anywhere with it. And just to be sure I mention it, one famous picture associated with that, with the quadratic case, is this one that's on the back of the book. So we'll make some connection to that picture on the back of the book, which is one of the, that's not the Mandelbrot set, that's the picture of period doubling and chaos. Stuff that people, sort of, it's like a third world that had been invisible for years. People imagined that things either converged to some answer, or they diverged, things blew up. But what sort of hadn't been seen was the possibility that they bounce around in a chaos, if I can use that word, in a chaotic way, a way that's very hard to give any formula for. But nevertheless, you can understand something about the average behavior or the limiting points, what can happen. It's this, if I mention a few of the other key ideas, it's this sensitive dependence on u0 that comes up. That is quite typical, and somehow it just, nobody had really caught on to that for such a long time. I mean, the example one here is you know, if a butterfly flaps wings, then that creates a little change in the air, in the circulation of the air in some tiny amount, but can that have a big effect weeks later? I don't know, to tell the truth, if it can. I mean, that, it seems like pushing it, but that's the point, that a slight change can produce big changes later. And actually, can I indulge in a little philosophy? Because, which I'm absolutely unqualified to do. But I naturally think the same about the history of man. Is our sort of human history sensitive to small changes? So that a little, if I change U naught a little bit, then after 100 steps, I'm just indescribably far away. I'm not near the two U100s are not close anymore. And so I don't know whether we, so it's somehow, it's deterministic, officially speaking. I mean, it's a formula completely determined, but yet it's so sensitive that even though it is determined, you can't predict. That's basically it. And I guess with weather, probably predictions now are, maybe you can predict pretty well for a week, but beyond 2 weeks, it's probably the sensitive dependence is taking over. So it's just a whole area of interesting mathematics, which actually began with weather. A guy named Ed Lorenz at MIT was used a computer, or this is years ago, so it would have been really slow, to solve some differential equations. His model of the atmosphere, 3 equations and 3 unknowns. And what he found was that they bounced around, and then they would stay in one loop for a while, and then in some erratic way it would go over to another loop. So it's a picture of the attractor is sort of a loop, 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 loop for maybe 100, maybe 1,000 times, and then it'll jump over, maybe go 417 times, and then jump back. It's quite striking. And you can see it on the computer quite readily. And now if I connect it, well, I will write something on the board in a minute. If I connect it to something classical, I would think of Newton's method for solving nonlinear equations. That's an iteration. That's a famous iteration. If I have a nonlinear system and I want to solve it, I use Newton's method. I'll write that down before the lecture ends. Just you know, Newton's idea is linearize wherever you are, and solve the linear problem, and that gives you the next guess. Well, that's an iteration. And where Newton's method will go, which answers it converges to, which not. Well, let me start with the simplest case, which will exhibit some of the possibilities, but it'll be simple. Okay, so what happens if I iterate that function? So that's a linear function. I'm just multiplying by a every time. So now, in that one unique case, I can produce a formula. What do I have after n steps? If I started from u0, and I multiplied by a every time. Just a to the nth, right. So now you can tell me what all the possibilities are. When will it, so what are the possibilities? It could converge to 0, maybe. So I'll call that u infinity or something equals 0. And when would that happen? When would this limit, this iteration multiplying by a every time, when would that go to 0? When a is less than 1. So for some cases, it'll less than 1. When would it blow up? When will we go off to infinity, if we allow ourselves to use that language? That would happen if a is greater than 1. Right. A is greater than 1. And notice I'm doing absolute value, because a could be a negative number here, but still what I've said would be still true. Now what about, are there any other possibilities? I could have just a steady, I could have a fixed point, so it just stays, or yeah, a fixed point. When would it just stay put? with A equaled 1. And we even have one more possibility, which is what? It could, so the only remaining A is minus 1. And what happens if A is minus 1? It would go U0 minus U0 plus U0 minus U0. It would oscillate. So it would be it would have period 2. Can I use that word, period 2? It would oscillate between a pair of values, plus and minus U0. Okay, so those are some possibilities that show up even in this simple case. I guess I can't resist always asking you about the matrix case. Suppose, so this is like time out to practice linear algebra. Suppose this is a vector. Everything is a vector and A is a matrix. So we're sort of doing a power method here. We're taking, this formula would still be true. Start with any vector, apply a matrix A, apply it again and again and again and again, and that's what you're doing in matrix iteration. So what we're about to answer is the most fundamental little bit of theory in iterative methods in linear algebra. Iterative methods in linear algebra. When do the things converge? Okay, so what takes the place of A? Here, that was just a number, and we could see that the test for convergence was the number should be smaller than 1. Now, what's the test for the matrix case? So let me just we use a little space here for the matrix case. Tell me the corresponding. If I have a matrix, I take powers and powers and powers and powers of that matrix. How do I know when those powers get smaller and smaller eventually? I mean, they might grow a little while, that's possible. But then when do they go to 0? The eigenvalues are the test. The eigenvalues are the test. So the matrix case, we would need all eigenvalues below 1. So that's quite an important fact. And it's, one, of course, powers of matrices, that's exactly what eigenvalues are just right for, because the eigenvalues of the 100th power are lambda to the 100th. So the eigenvalues like bring us back to the scalar case. That's what eigenvalues do. I'll just comment that in recent years, there's always something new. So some people are paying attention to the fact that, well, it's true, if the eigenvalues are smaller than 1, for example, let me just write an example here. 1/2, 1/2, 0, 1,000,000. Okay. Okay. Or maybe I'll make it 3/4 just to pep it up a little. Okay. Now, the powers of that matrix, so this is my matrix A, what happens to the powers of that matrix? Do they go to 0 or not? Well, you can see the eigenvalues of that matrix because it's a triangular matrix. That means that the eigenvalues are sitting right there on the diagonal. So the eigenvalues are both, it happens to have a double eigenvalue. It's certainly smaller than 1. So the answer is yes. We're in this convergence to 0 for all, the powers of that converge to 0. But those powers might grow for a while and then decay. And so there's some information, not, the eigenvalues don't give you total information is what people are saying. And the idea of something called the pseudo-spectrum has been pushed by some analysts. Okay, but as far as eventually, that will go to 0. Okay, and blow up, when would the powers of the matrix blow up? Well, if any eigenvalue is bigger than 1. If any eigenvalue is bigger than 1, then the 100th power will have this eigenvalue to the 100th, getting bigger and bigger, and the matrix has to get bigger and bigger. Right. When would we have fixed points? Let's see. When would it, well, the identity matrix would certainly do the job. I'll put A equal identity. I didn't really think through this. See, as soon as you get to matrices, there are some new questions. What about, well, you can see what's the marginal case here. I mean, the marginal case, which is all these and whatever possibilities might arise, is what? The marginal case would be when some eigenvalue has absolute value 1. The largest. No, if any one is bigger than 1, then we take off. But if one eigenvalue or several eigenvalues have absolute value exactly 1, like an orthogonal matrix, all the eigenvalues have absolute value exactly 1. And you can see, suppose the orthogonal matrix is a rotation. Typical orthogonal matrix just rotates the space. Then I rotate and rotate and rotate, and I sort of wander around. We have an attractor. Maybe that's a good example, where you'd have an attractor. All the U infinities would kind of be would kind of be a set that it would wander around in this attractor. It wouldn't blow up. It wouldn't go to 0. It would sort of approach this attractor. Anyway, even the matrix case already, so I'll just put some lambda equal 1 down there as just to kind of complete that list, but not a very specific. I didn't fill in all the details there. Okay. Now, ready for nonlinear, which is the reality here. Okay, so can we get an idea of, if I iterate, let me take an example then. Second example. So my example is going to be AUN minus, so that has a linear part as before, but now I'm going to put in a quadratic part. This is a great example, where A is a number, and I'm interested in what happens for different A's. So A is a parameter here, and the question is, what happens? I hope everybody sees that you could just write a little code. 3 lines would do it. Input A, input U0, and let it run. And then you could decide, does it blow up? What does it do? And you could input different U0s and different A's, and we'll see that as A changes, so A is this critical parameter, which we already saw in this case, that as A changed, we got different behavior. Now it becomes more interesting. Again, if A, so let me take a typical A, somewhere between 1 and 3 is a typical A. What will happen to this iteration? Can I try to draw it? I guess if it converged, what would it converge to? If it converges, if the UNs approach something, what equation has to be solved by that limiting point? So this is the idea of iteration. I can remember, actually, this came up in my first consulting at Lincoln Lab when I was an instructor at MIT. I came out and was involved with scientists who established an iteration. And the first question was, well, if it converged, which it seemed to do, what's the limit? Okay. Sorry? Sorry? The left side would match the right side. If as n goes to infinity, this thing goes to, should I call the limit? Let me call the limit, rather than U infinity needing a double symbol. Can I use capital U I'll use capital U for the limit, if it exists. So if, here's the important point, if un approaches capital U, and of course then un plus 1 does too, then the left side is approaching capital U and the right side is approaching, well, whatever it is. Then AU minus AU squared. Good. So there's an if here. But if it converges, then it's not hard to figure out that we can identify what the limit is. Actually, what's up here? So what could capital U be? We got a second degree equation now, so we got two possible limits. Let's see. We could have U equals 0, right? That's one possible approach. It could approach that, or what's the other U that it might be? If I divide through by U let me divide through by U, 1 equals A minus AU above. That's so I've knocked out the U equals 0 root, and the other root of this quadratic is, let's see, if I put this, yeah, is it 1? Yeah, if I put this, do I get A minus 1 over A? I think that's what I get. Yeah. Actually, bring the 1 over there, so I have A minus 1. Bring the AU over here, and then divide by A. So that's, okay, which does it approach? Or neither. That's our simple question. Does it approach U0, or this thing, or does it blow up? It can't approach anything else, because if it approached something else, then that's something U would solve our equation, but we've got the only solutions. So how to tell? Let me think about. Let me draw a picture. Oh, so here's the crucial picture in the whole subject. Okay, here's U, and here's f of U. Okay, which is AU minus U squared. So I'm just going to graph AU minus AU squared. Start with that. All right. So that's a parabola, right? And it starts at 0. And where does it end? Where it comes back to 0 at 1, right? At U equal 1, I'm back to 0. So it's a parabola. Oh, it's just a parabola that sits on nice symmetrically between 0 and 1. Okay, so that's graphing U. That's f of U. That's just my thing. Okay. Now let me graph this iteration. So let me start at a point U0. The nice thing is we can stay inside this interval between 0 and 1 for this example. Okay, so let me start at some U0 and follow the iteration. Okay, so where's U1? How do I find U1? I take f of U0, so what do I do in the graph? I go up to, there's f of U1, right? Is that right? Yes? Okay, and then I have to think, what do I do next? I'm taking an A, okay, so now that's U1. What do I do now? Do I have a feeling I want to go over. Yep, I should have practiced this. So somehow, if that height is U1, then my new let me somewhere there is U1. I'll figure out in a minute what these dopey lines I'm supposed to draw are. Actually, I'll cheat. I'll look to, because I'm sure I did it. Yes? Okay, so why did oh yeah, Yeah, the good figure has a 45-degree line in it. You're absolutely right. Here's the line, 45 degrees. Okay. That's 45 degrees, okay? So now let me remove that ridiculous U1. All right, let me get this figure right. Okay, so why did I draw that 45 degrees? Because if I go over to that 45-degree line, say to there, where it hits the 45-degree line, then that should be U1. Is that right? That height is U1. So when I go along here, that's the point U1, right? It's on the 45-degree line. So this is the point. Let's just stick in a few. The coordinates of this are U0, U1. Because it went along U0 and up, the height up was U1. Coordinates of this guy are U1, U1. Okay, so I'm at U1. Now what? If you'll take one more iteration for me and get U2 in this picture, I'll be a happy guy. So how do I get to U2? Up to the curve, right? It's across, up, across, up. So here I'm at U2, U1. So I evaluate. F of U2, U2 is F of U1. That's the rule. So I go up to where that is. Good. And now what? Now I know U2, so I go along the 45-degree line and then I'm at U2. And then there is U3. Am I okay? So I don't know what's happening here. It looks to me like maybe this isn't going to converge. Do you see what's happening here? It's like we have a little spider web. The rule is start wherever you like, up across to 45 degrees, up across to 45 degrees, up or down to the curve, across to 45 degrees, up to the curve, across to 45 degrees. And the question is, does our little spiral, a little sort of square spiral, converge in to... Now, what's so special about that point? Why is that point? That's the point where the 45-degree line intersects the curve. That deserves a little bit of yellow, right? What's so great about that point? That's the point where the 45-degree line hits the curve. It must be capital U. Because that's the point where the 45-degree line is capital U, and the curve is AU minus U squared. And that's the equation that gives U. So it's quite fun to see, does this thing spiral in or does it spiral out? In other words, what we now want to decide is this a stable point where iteration goes into it, or is it an unstable point where iteration goes out of it? Let me just, and this was another capital U, right? That was our other candidate. That was the other U was at 0, because that's the other place where the 45-degree line and the curve meet. So they meet at 2 points, there and there. And what do you think about the stability or instability of this one at 0? What's going to control the instability if I start near 0? Yeah, let's draw a blow-up picture of this guy, because that we certainly ought to be able to pin down. So here's my 0 point. Here's my 45-degree line. And here's my curve, and it seemed to be starting off like that, going somewhere. Now, is that point, that would be one possibility. Another possibility would have been for the curve to stay under the 45-degree line. This would be, I think this is an A probably bigger than 1. and this would be an a smaller than 1. Oh, yeah. Can you see which of those pictures is going to give me stable and which is going to give unstable, converging to that, to this capital U? The U happen to be at 0 where we can spot it. So what happens here? We start close. We go up to the curve. We go over to the line, up to the curve. We're leaving it unstable, right? This is unstable. We're not going to settle in on that because every time we get close, we get further away. What about this one? We start here. We go up to the curve, over to the 45-degree line, down to the curve, over to the 45-degree line. What's happening there? Stable. And what's the difference between the two? The difference is that the derivative, the slope is bigger than 1 there. Here, the slope is less than 1. That's what's happening. Unstable is when the slope is bigger than 1. And here, stable is when the slope is less than 1. I'm already here on top of the main ideas. And I can't resist bringing it back to the linear case. What was the slope when this was f of un? What's the derivative when f of un was just a times un? The derivative is just a, right? The function is au, and the derivative is a. So there we saw this same fact, that if the slope was smaller than 1 at the 0 point, it went to it. If the slope was larger than 1, it took off. So that's just what we're seeing here in a picture that's locally the same picture. If I microscope in, zoom in around here or here, I'm seeing just a totally linear picture. But the nonlinear part, the fun starts when it gets away from this point, and the question is, where does it go to? So finally, I'll put in absolute values there because the same would be true if the function was going downwards. Well, as it is there. Here our slope, at this point we were interested in. So the big question is, what is f at f prime, the derivative at u? That's the decider. F prime bigger than 1 decides unstable, it won't settle in. F prime less than 1 decides stable, it will settle in. Okay, so we have to find f prime of u for this quadratic case now. Okay, so that we can do. We have this formula for this. Here's our u. This is our u. So now can I plug it? Now I have to find f prime at that point. So what's f prime? Guess we could even figure it out. So here's my function au minus au squared. So the derivative of that is a minus 2au, right? That's the derivative. And now I'm plugging in, I want to know at this particular u. So this is a minus 2a times a minus 1 over a. And fortunately, the a's cancel. And what do I have altogether? Maybe there's a 2 there. So forget that. So I have minus 2a minus is a 2 plus an a. I think it's just 2 minus a. I think that's what we got. Okay. That's the slope, which controls stability or instability at this one. The slope here was just a. The slope here was just a. At u equals 0, this just boils down to a. Okay, so tell me now what's up. Tell me the possibilities. So we might have a between 0 and 1. then what will happen to the UNs? Next, I'm going to say 1 between A between 1 and 3. And I want to ask what happens to the UNs. Okay. Okay. So suppose, first of all, A is small. Suppose, first of all, A is small. Then what's our picture? What's our little parabola loop when A is small? Okay, if A is small, the parabola is small. It just is down, it's creeping down here. And so what's the limit point then? 0, right. So UN goes to 0, which is a nice stable point because the slope is, because F prime is exactly A. And it's less than 1, and that's all great. Now, what about if A is a little bigger? Suppose A moves up. Suppose A moves up to 2. You could execute this iteration with A equal to 2, and what would happen? Or A equal to 2.5. Suppose A was 2.5. All right, suppose A is 2.5. What will happen? Will it converge to the origin, to this solution, where that is a solution? The curve meets the 45-degree line right there. Will it converge when A is 2.5 to this guy? Yeah, so it'll go to this one. Why won't it go to this one? Because the derivative here is A, and if A is 2.5, that's unstable. Why will it go to this one if A is 2.5? Because we figured out the derivative, and if A is 2.5, the derivative is -0.5, so it's going down like this, but slowly, and it's stable. You see, everything's like critical. The question is that slope at that crucial point steep or flat? If A is 2.5, it's still pretty flat. The slope is only -0.5. That's okay. It can zoom in. But it looks like, the way I've drawn it, it looks like I've got a slope bigger than 1, and it's not doing what we want. So what will it do? To complete this, for A between 1 and 3, we got this F prime is 2 minus A, and it's smaller than 1. Okay, so it goes to this limit A minus 1 over A, this winner. Okay, and now comes the real question. What if A passes above 3? What does this iteration do if A goes up above 3? You see, you can say, oh, okay, Professor Strang has just cooked up this problem, and now he's making a big lecture out of it. But it's the perfect model for iteration, where there's some nonlinear term in it. We've got now, instead of just a very limited range of possibilities, we're going to see more possibilities. And right now, with A bigger than 3, so 3 between A and there'll be some next limit. It happens to be about 3.45. What's up? What could it do? It can't approach that, and it can't approach that, because it's the case of my figure here. When it's steeper than 1, it moves away from that. So, right. So oscillation. Okay, it's going to bounce somehow. And now, what do we mean by bounce? This case bounced, right? When A was -1, it bounced between 2 points. So it had period 2. That could happen here, and I think the answer is yes, that is what happens here. I think I think it bounces between 2 points. And how would you plan to figure out what those 2 points are? I believe it has period 2. So I believe that it in the limit, of course it, so what does period 2 mean? So it means that, of course, it's not going to, in this case, it bounced exactly from u0 to minus u0 to plus u0 to minus u0. There wasn't any limiting process. It did it right away. Up here, it's going to, it's not doing it right away. It's gradually, this web is unfolding until it comes over to some other guy, probably, and it's trying something there. Well, I don't know what's happening there. This point has become unstable. It's not going to, that's not going to be one of the 2 points. Oh yeah, because I guess my wording made it sound like maybe that could be one of the 2 points. But no, it leaves there. Once it leaves there, it doesn't like that point. That's what's the opposite of attractive? Repulsive, right, repulsive. That point is a repelling point. That's not going to be a limit. But what will be a limit will be 2 attractive points. But what are they? Well, if we've got period 2, we're looking, what are we, a period 2, we're looking at a limit point of what? Here's the key idea. We're looking at a limit point, if we have a period 2 limit point, what are we looking at? We're looking at f of f. F of f. If we do 2 f's, then it's a regular period for 2 f's. So that's the thing. For period 2, I would have to I would look at the iteration f of u. N would be un plus 2. And I would look at that iteration, just the even n's, right? u0, u2, u4, u6, and so forth. And then the u1, u3, u5, u7, they're going off to some other guy. So those are the 2 that it's bouncing back and forth. So I have to draw f of f. And can I draw that? Well, I had enough trouble drawing f of u, but that was a parabola. Now what will f of u look like? Well, we know roughly what it looks like. Let's see. Can I draw f of u? Tell me what sort of a function I've got here. So it's f of u. What do I mean by f of u? There's f of u, and then I should plug in f of u, so it would be sort of a times au minus au squared minus a times au minus au squared squared. That's f of u. Right? Because there's f of u, and I plugged it into f. So it's 4th degree. So it will look something like this. It'll go up, down, up, down. It'll have like a potential well, so to speak. Let me try to improve that picture a little more so that it does what I hope it does. Okay. Now, this is our function, f of u. And how do I decide, does it converge, what to, all that stuff? Well, the same way. Here's my function. I draw the 45-degree line. Oops, try to make it straight without cheating too much. So it's a 4th degree thing. So it's got 4 roots. And would you like to tell me 2 of them? 2 of the roots of this f of u are, well, one is clear, 0. And what's another one? Another one will be this guy, right? Because that solved y. Yeah, it's kind of neat to see why. It solved, it was a fixed point. F of u was u. So if I do f again, I'm still at u. So this was these two guys, and that's this one here. Those are the two that we already found. U equals 0 or a minus 1 over a. Those are the two. But now it's a fourth degree thing, and we've got two new ones, which we could figure out. And here's the point. Now I'm ready to give the whole picture. This guy is now unstable. A has got too big. These guys are stable. Those are the two that it bounces between, those two values. If I start, yeah, is that right? Yes. If I start here if I start near here, no, what happens if I start near this point? I start near this point. Where is U1? Well, this was the one. U1 will be near this point. And then if I apply F to U1, that's applying F of F to U0, so I'm back here. So U2 is here. And anyway, I'm converging to this period 2. So this is this idea of period doubling. Period doubling. And let me give you the whole picture for this famous, this is sometimes called the logistic map, because it came into, for differential equations, it's a highly important differential equation. If it was du dt equal this, that's a predator-prey, that's the nonlinear problem that people study like mad. If it's du dt equal this, then depending how much this is like growth, this is like, yeah, you get food, you do good stuff. This is a negative term, so that like if there's too many people, yeah, actually maybe that's since we just have one variable, it's not predator-prey, it's just population. This predicts the population of the Earth. Not that badly, actually. So there's some magic number A that has to do with when U is small, then UN squared is extremely small. So when there were, like 10 people or just Adam and Eve or whatever, there wasn't much there. So the population grew. It grows. The population of the Earth grows for a while, and then at some point, this stuff begins to slow it down. And so the solution to that is this like famous S curve. So I'm off onto the differential equation, and the whole point is that the differential equation doesn't have any of this funny stuff. So people who classically study differential equations, the population increases for a while with a slope A, and then it has a pretty steep increase and then it slows down, and I think the limit is estimated to be what, about 10 billion or something? I think the limiting population of the Earth is somewhere around 10 billion, and we're somewhere perhaps above, are we above 5? Yeah. Yeah. So we're near the end, right? Well, you and I won't live to see it, but we're somehow going to have to slow down, which everybody knows. Okay, so that's like the differential equation case, and contrast that with the iteration, the discrete case, where so many new possibilities appear. And that's sort of what people missed, because, in calculus they could solve differential equations 50 or 100 years ago, but this, you really have to execute. So what happens? I promised to say in a few words what does happen. As A increases further, these become unstable. As A increases, the slopes get steeper and steeper. As A increases, everything gets steeper. So these go unstable too. So there's no stable period 2 cycle to converge to. Well, what can happen? Well, you think, okay, it probably changes to period 4. And you're right. So at a certain point around A equals 3.45, it goes to period 4. If I graphed F of, which I don't plan to do, if I graphed F of F of F of F of U, I would, I'd have it, it'd go like this, and my 4 points would still be on it, but they would be all unstable, and there would be 4 stable guys, and that would be the period 4. And then I keep going. Increase A, and that's what you're seeing on the back of this book here. So period 2 is coming out of the bottom of the book, and it splits into period 4. So across here is the well, at the lowest part of the book. See, I didn't have a big enough book to start at A equal 0. So the book really picked up around A equals 3.3 or 3.4, where there's a double period. And now as A increases, I go up as A increases, and then you get period 4 and then period 8. But then quite amazing stuff happens. So that people don't really yet know everything in this picture. So what's plotted, a white point means a stable attractor part of a period. So you get 2, 4, 8, 16. But the thing is, you get to 2 to the 100th, 2 to the 1000th, and A is only increasing by a little bit. So that after you've got all the powers of 2, you still don't know the whole story, because A is only up around, I've forgotten where all the powers of 2 are in this picture, but maybe just probably says here on the side. Anyway, we've got more A's to go. Yeah. Oh, yeah. Okay. Oh, all the way down here. So here's period 16, 32, 2 to the infinity. Just quit there. But now let A go some more, and something else has to happen. And there's a period 6. I don't know if you can see. There's a particular point where there would be exactly 6 points along, and then 12, and then 24, and then 48, and so forth. And then up. Then we start up, and then a period, odd period showing up, period 5, and then here, way up here, for A near up near 4, a period 3 shows up, and they follow a particular pattern, of course, so that even though the details of the picture are completely difficult to pin down, the overall picture of the order in which periods appear is kind of universal. But there's more to it. There's values of A that don't have any period at all when we get up here. There are values of A for which there isn't a period. And then that's the chaos. That's where chaos is. That's where there's no limit. It just jumps around forever in a totally erratic, pseudo-random way. Well, I should say deterministic, but pseudo-random. So that's this logistic map. And sorry, all those period guys. So this was stable. This period 2 for that range of A's.
Where is it unstable?
I don't think our eyes are able to spot it, but
Where is it on the book?
I think it's hidden in some of those lines. See, I've identified yeah, the text would add more to what I'm able to say, but there will be lines there which we can't pick out by eye, where there isn't a period, where it's chaotic, and that's typical. It's just so this very simple map has exhibited period doubling in some universal way, and then also has exhibited chaos in some universal way. And there's a guy named Feigenbaum who was at Los Alamos, and he figured out some Feigenbaum constant, which again was universal and controlled what was happening. Now, I don't want to see the time run out before I mention fractals and Mandelbrot set. You know Mandelbrot's name. So he realized that a lot of curves, a lot of boundaries in reality were not just nice smooth curves, not just like one-dimensional curves like a curve like that, but had higher dimensions. Not dimension 2. Dimension 2 is like the dimension of the plane, but had some fractional dimension. So he christened those fractals. So he's originally French, came to IBM, spent some time at Yale, some time at Harvard. He's a difficult guy, actually. I remember having dinner with him once, and just in a group, of course, and he totally dominated the conversation. You know, it's okay I mean, he's a wonderful, lots to say, too much to say. I'll leave it there. Okay, but I have to, but what he did revolutionized this theory of iteration. So I'm going to leave the logistic map with a real variable and go to xy, to complex variables, because we've just been using complex numbers. So the iteration now is going to be Zn plus 1 is Zn squared, the quadratic, plus a constant. Well, you say, boy, if you can't figure that out, you know, what do you pay mathematicians to do? But it's incredibly complicated. So we could ask two questions. We could ask now C is like our A before, that we vary. So for a particular C, just like a particular A, we could solve this equation, we could see what happens for a particular C. For a particular C, we could see what happens to this iteration, right? If we took C to be 0, we could probably figure out real fast what happened. Yeah, what will happen if C is 0? Well, it'll depend on the starting point, right? If C is 0, so forget the C, then I'm just squaring every time. So it depends on the starting point, right? So for each C, I could I could draw all the z0s for which Zn stay bounded, for which the z's stay bounded. Okay, just tell me what that would be for C equals 0. If C is 0, which complex numbers starting with z0 would this iteration stay under control? It would be the unit circle, right? If z0, because we're squaring every time, so if the original start is inside the unit circle, then we're taking powers and powers and powers, okay. And this would be called the Julia set. So these were actually studied, again, by a Frenchman. That's his last name, not his first name. Quite a while ago, you know, classically, 100 years ago, or 80 years ago. So that's quite interesting. And these sets are quite remarkable, and that's the sort of thing we're doing now. Mandelbrot's idea, with which I'll close, so the Mandelbrot set was, let me show you what the Mandelbrot set looks like. So Mandelbrot just looked at it a little differently. So Mandelbrot's idea is start at z0 equals 0, always. And he plotted the C's. You see that little twist? This one had a different, for each C, we have a Julia set. Okay, now over here, C is the parameter. We start, let's say, at 0, and we plot the C's for which the iterations stay bounded. Same idea, for which the Z's, for which the Zn's that follow stay bounded. So we're plotting the C's for which our iteration stays reasonable. And the plot of those C's, C could be a complex number, of course. We're really in the complex. So I could write it in terms of X and Y. So we have Z has a real and an imaginary part. So this is a quick way to get two equations in two unknowns. And this plot, well, I guess I'm hoping, because I'm feeling bad that I didn't bring the picture of the Mandelbrot set. I'll bring it next time, this book of Mandelbrot sets. But maybe many of you have seen it. Should I try to draw it? I mean, I'll totally fail, right? But it might remind you. It sort of has funny. Oh, perhaps I put it in the book. Oh, it's in the book. Yes, good. So there is the famous Mandelbrot set looked at, at a distance. So these the origin is somewhere here, and the black ones are the points, are the C's for which it stays bounded. But the point is that the boundary of this, that it's so delicate. If I'm near that edge of this Mandelbrot set, and I just change C by a tiny, tiny amount, it may be out of the Mandelbrot set. The boundary between in and out is a fractal. It's like an incredibly complicated coastline, and people can compute the dimension of that boundary, and it's somewhere between 1 and 2, and this is the kind of, so this figure is the kind of figure you get by zooming in. You see a little bit of just incredibly complicated, and if I zoom in on that, I see even more complications. So it's this zoom and zoom and zoom. It's sort of like self-similar. No matter how much I zoom in, I'm seeing new stuff or seeing complications, and that's a feature of the fractal business. Well, okay, so that's taken our lecture 11, a sort of blue sky lecture, if you like, but it certainly makes this point that iteration is more unpredictable than you would think, and that of course most numerical methods are iterative. To compute eigenvalues, we iterate. We'll discuss maybe the QR iteration for computing eigenvalues. For solving linear systems, for solving nonlinear systems, we use Newton's method. And I'll put in the notes suggest one or two of the exercises that have produced terrific pictures. I mean, you could produce these pictures, just testing an iteration to see whether what limit it approaches. So we have, there's a whole world here of iterations, and we see in the discrete case, we see the complexity already in one variable, Then we see Mandelbrot level complexity in 2 variables. And in the differential equations, Lorentz had to go up to 3 variables. His was a nonlinear differential system of 3 variables, and it was just an extremely original observation. He must have, just let his computer run and plotted the thing and started thinking about what does this mean, and it led to a whole new branch of applied mathematics. Okay, so that's lecture 11. Lecture 12 comes back to partial differential equations, the heat and wave equation, just to see how they compare with Laplace's equation. Then we will have the 3 big types of PDEs. Laplace's equation, elliptic; heat equation, parabolic; wave equation, hyperbolic. Yeah, so you should really see how those 3 differ, and that'll be lecture 12. Okay.